Hello, this is Professor Yagobi. Today we're going to be talking about rotational motion. Alright, so our problem is set up as an inclined plane on a 70-degree angle. Alright, the problem is asking for if there's a ball rolling on the inclined plane, what is the minimum coefficient? It would be static friction, since it's of static friction, so that the ball doesn't slip. So in order to solve this problem, we are going to put the ball, the sphere, or actually it's a cylinder, at the top of the inclined plane, and we're going to set the mass is equal to 1,000 kilograms, which is given by the problem. Okay, let's first draw out our vector diagram of the forces acting on the ball at the top of the sphere, if it was to be rolling down the sphere. And for this problem, it's simplest if we set it up as rolling down the sphere, rolling down the inclined plane, so that we can easily solve it. Okay, so we have mg acting down on the ball. We have force normal acting perpendicular to the inclined plane. Then we'll have mg sine theta going down, pushing the force that's pushing the ball down because of gravity. And then we have the force of friction acting against the greater force of gravity pushing the ball down the inclined plane. Okay, next step, let's write out our relevant equations. So we know that I is equal to 2/5 mr squared, and we know that the torque is equal to Fr, which is equal to inertia times alpha. And we know that this alpha is equal to A over R. And our last equation would be force due to friction is equal to mu times force normal. Okay, now that we have all of that, let's start solving the problem. We're going to begin by noting that the sum of the forces is equal to ma. And the sum of our forces for this particular problem, which we can take from the vector diagram itself, is going to be mg. It's going to be mg sine theta minus the force due to friction. Okay, we can simplify this. The next step to the problem would be inputting a different, solving for the f. We can solve for f by setting it, by simplifying our equation Fr is equal to inertia times alpha. Solve for f, so divide by r, we're left with f equals I alpha over r. Now let's plug that into our equation. Mg sine theta minus before I go on, I need to note that the f can actually be further simplified by plugging in for all of for everything. So that I would actually end up becoming 2/5 mr squared divided by r times a over r. And we know that this is going to cancel this, and this is going to cancel this, so we're left with 2/5 ma. So now let's plug that in, 2/5 ma. And we know that this will end up all equaling to ma. Now what we're going to want to do is solve for the a, for the acceleration. We can do this by minusing this from here, which leaves us with 7/5 ma is equal to mg sine theta. Then we divide this here. Cancel. And we're left with a is equal to 5/7 times g sine theta. Okay, so now that we have the acceleration, we should once again note that we solved f is as equal to 2/5 ma, and now we should say that the force of the friction is less than the F of the LS, and that's going to come out to 7/2 mg sine theta is less than mu static mg cosine theta. Before I go on, I made a mistake. I need to explain how I got this here. And I got the total F, by solving for this. F is equal to 2/5 m, we got from here, and then you plug in the a, which is 5/7 g sine theta, and that's going to leave us with 2/7 mg sine theta. So now I can go back to this. 2/7 mg sine theta must be less than the force of static friction, which we know is equal to mu times Fn, and we know our Fn is equal to mg cosine theta, since this right here, mg cosine theta, and those forces are the same. Mg cosine theta. Now we just simplify, and solve for mu. This times mu s, because force due to friction is Fn times mu. So we're trying to solve for mu. We divide this whole thing by this. These cancel out. This becomes 2/7 tangent of theta is equal to mu s. And we know our tangent, and we know our theta is equal to 70. So 2 divided by 7, tan of 70. And that gives us an answer of 0.785. Okay, let's move on to the next part of the problem. The next part of the problem is asking us to solve for the speed, the final velocity of the ball at the end of the inclined plane if it had rolled down. And so we're going to do this by solving basically for work. And we know that work is equal to the change of kinetic energy. And we know that that is also equal to Fd. So our change in K is equal to half mv squared F minus, when using the equation in terms of inertia, it's going to be plus I angular velocity squared divided by 2, or times half. Now we know that we know what our inertia is, and we know that angular velocity is equal to v squared over r squared. Make note of that. Now we're gonna plug that in, so we get this is equal to half mvf squared plus half times 2/5 mr squared times v squared over r squared. We cancel those r squared. We're left with half mvf squared plus 1/5 mv squared. Now we further simplify by adding the two like forces, the two like things together, so that this would be 7/10 mv squared. We're going to set that equal to Fd. Then we're going to set this again equal to mv squared. What we were talking about earlier, it's the sum of the forces, which is sine theta minus mu g cosine theta and isolate the v variable, dividing this by 7 over 10 m divided by 7 over 10 m v squared becomes equal to 10 times sine theta minus mu g cosine theta all over 7. Take the square root of that, square root of that. V is going to be equal to 10 times sine theta minus mu g cosine theta all over 7. And by plugging in 1000 for, by plugging in 9.8 for, okay, I forgot to make this m here. This m here. By plugging in 1000 for m, which was given by the problem, and 9.8 for g, and by plugging in the mu that we found earlier, which is 0.785, we get that v is equal to 96.938. Okay, on to the last part of our problem. The last part of our problem asks to find the work on its way down of the cylinder. Once again, we're going to note our important work formulas, which is work is equal to change of kinetic energy, which is equal to FD. And we're also given that V is going at a constant 5 meters per second. The first thing I want to do, which is asked to do by the problem as well, is find the height of the actual inclined plane. And we're going to do that by using the information given. Another info given would be the change of time takes for the ball is 4.5 days. Okay, we know that the change of x is equal to v times the change of t. And we know our change of x, so we know our change of x is going to be equal to 5 meters per second, or 0.5 meters per second, times 4.5 days. And when you convert 4.5 days into seconds, which is required by the problem, in order to solve the problem to put everything in like terms, since we're using meters per second, you get 800,000. And this is equal to 194,400 meters. But this is just the hypotenuse of the inclined plane. So, in order to find change of y, we're going to have to times this by the sine of 70. So, 194,400 times sine of 70 degrees gives us the answer, which is 150,444.348 meters for change of y. Okay. But all of this isn't really necessary because the problem is actually a trick question. Since the ball is going at a constant velocity, we know that F is equal to ma, and since it's going at a constant velocity, there is no a. It's in equilibrium. So a is equal to 0. So our force is equal to m times 0, which is equal to 0. And we know work is also equal to Fd. And so if force is equal to 0, it doesn't even matter what the d is. The answer is 0 joules. And that's how you solve everything out. Thanks for watching my video.